Hello everyone, and it's good to have you here again. So, I will be talking today as a follow up on the last week presentation in which I talked about transformers in depth. So, I am going to share my screen, just because we need screen share anyway, but I'm going to my aim for this presentation today is it's going to be more interactive, so more practical actually. So I want to show you a simple demo about transformers, and just walk it through together. Something I've prepared, I've worked on in the past, but I want to show you how you actually use a transformer. But before we do that, I want to just do a quick recap of the discussion last week. So let me share my screen and then we can start. So I'm going to share my entire screen. I hope it's going to be readable, but let me know otherwise, and I can try to maybe increase font size. You can let me know on the chat on the side. So yeah, just keep this open somewhere just so that I see if someone uh, say something. Right. Right. So, what we talked about last week is this diagram in detail. This is the architecture of a transformer, which is going to be, it's super famous now. It was part of the Attention is All You Need paper, and we talked about it in details last week. So we talked about the embedding part here, and then the encoder. This whole thing is the encoder, and then the decoder part as well. So, and then the attention and all these things. But to recap, essentially what a transformer does is that it kind of try to encode your input into some hidden representation and then decode it to some another representation. That's kind of the gist of what a transformer is. So if you recall, we talked about how, say for example, a translation can be done within pre-transformer. We talked about the idea of having a neural network, a many-to-many neural network, in which you could have like your source sentence being fed into the recurrent neural network, and then converted into some kind of hidden representation, and then you start from the hidden representation, try to decode that hidden representation into your target language. So it's more like trying to kind of like make that hidden representation kind of represent the meaning of your sentence, which allows you to then translate it to a different space, which is the target language. Essentially, transformer is the same as we said. Essentially, it's kind of like an encoder, and then you have your decoder here, which, for example, generate targets, sentence. And in this particular demo, it will actually be about translation. But I really would like you to think about transformer as not just translation or NLP in general or classification. It's a lot more than that, because anything that anything that can be anything that can be a sequence to another sequence is a transformer. Anything that is a sequence to something, like in this case we say, for example, sentiment analysis, that's also a transformer. So as I mentioned, maybe in the during last week, one unexpected application of transformer was using it to do integration. So you have in mathematics, you have, say for example, you have differentiation and integration, and integration is known to be a difficult problem, a challenging one. So they used a researcher from Facebook used transformer to do mathematical integration, and it worked quite well. But yeah, the focus of this will be about neural machine translation. But I would like you to think out of the box when you try to apply a transformer within your day-to-day exploration or learning. Yeah, so the encoder part here, let's quickly recap. You have the embedding here, which converts your input statement into some n-dimensional vector. Obviously, the more dimensions you choose, the more freedom you have, the more powerful your representation could be. And then you have the attention here, which is going to be kind of like trying to attend to different part of the statement. So just write something here. So for example, if you say I'm just going back to my example from previous week. So I have a cat at home. It is sleeping now. So attention is going to be the mechanism which allow it to attend to cat. That means they have a relationship. The it here refers to cat somehow, and that's kind of like the power of transformer really is imparted due to the attention mechanism here. And then again you have in the decoder again, the remaining of this is, as we said, like normalization, just to make sure that your numbers aren't like too large or too small, making training difficult. And feed-forward network is the typical one you see. In the decoder you see you have the attention here mechanism, and that's again attending to the output of the decoder itself. And then you have another attention layer based on the input of the encoder, and that's the difference between a decoder and encoder, because you want to be able to say that I have my input statement, and I would like, based on it, I would like to generate some output. And this is why you see an extra layer, because in the encoder you don't have any input just yet. You're trying to understand your statement, but the decoder is the one that's going to generate a statement, and while doing that it will need to attend to itself and the input from the encoder. So yeah, I don't wanna spend too much time on this. I share the slides. I would encourage you, if you haven't attended the presentation from previous week, I would encourage you to just go through these slides, and I will also share another valuable reference actually later, so that it's gonna help you to understand the transformer. But yeah, let's get started with this practical demo I want to do, and I can share this with you. Maybe I will add it to my GitHub, and then you can I can share the link so you can try it yourself. But so let me just start walk you through it, and then kind of like explain what every cell is about. So this one is like, I'm gonna walk you through this, like these number, the dimension and embedding, etc., and max sentences. But in particular I want to talk about bucketing as well. But for now, let's just ignore this. Let's talk about from the second cell here, which is loading training data. So I'm using PyTorch here. PyTorch has a package for NLP, so you can take a look at it. It contains multiple things. One thing that it contains data sets. So no, sorry, I wanted the torch text data set. Just want to see if anyone wrote something in Discord. Cool, thanks Tyler. Yeah, so PyTorch has this sub package called torch-text, and it has multiple data sets you can play with. In this particular demo, we're gonna work with the machine translation one, and we're gonna use the IWSLT 2016 translation. So this is a data set that is known, in the NLP community. It contains translation between multiple languages pair. We're gonna use the English to French one in this, and then the way you download this is you use you import it, and then you download it with you create the object here, and then you specify your language, source language and target language, and then you decide which data you want. So you could say either training or validation or testing. So I'm loading training and validation test, and I'm printing something, just an example. In general, it's a good idea to print example of your training data set, because you want to know what what data you're actually dealing with. So you're gonna see how when I walk you through this, you're gonna see how we end up converting all these kind of like textual data into numbers that can be fit into a transformer. A bit hard to see the screen with a small font. Yeah. Yeah, it's not actually two screens. It's actually one screen. It's just a wide screen. So let me try to zoom in a little bit. Is that better? Okay, yeah, and I see a question here about about encoder and decoder, etc. I will answer that later of why sometimes you use an encoder or decoder or both. Yeah, so I'll talk about that later. In fact, actually, let me just talk about it briefly now. Just otherwise it might uh, leave some confusion here. So the idea is that if the encoder, if you think about it, is that it's taking some input and then converting it into some hidden representation, and then you can do whatever you want with that. And so it's more like it's taking an input and generating some hidden state. So it's more like trying to understand what the input is, while the decoder is a generator. So if you think about, for example, if you're trying to do a sentiment analysis, if you have some customer reviews on Amazon and you want to be able to automatically detect the sentiment of a customer review, then that's really just an input, and the output is like a one or zero based on happy or unhappy, positive, negative, or you could have maybe five. But you can see this is the nature of just an encoder, where you're taking something and encoding it. The decoder, on the other hand, is to generate something. So it starts with something and then generates some other statement. So you can think of decoder, for example, in say ChatGPT. GPT models are all decoder based. So the way you're doing this is giving it some statement and then generating something for you out of nothing. Well, I mean, not out of nothing, out of understanding what your statement is. So it takes and try to do autocomplete on it. Or for example, think about GitHub Copilot. Many of you might have already used it. You're writing a comment and it generates code for you. So this is a decoder only. Now, when you want to have encoder and decoder, when you want to use them, is when you have an input sequence and an output sequence, and that's when you need both of them. So in the slide I mentioned, I had a slide last week where I could say, like, use the encoder only if you have like three scenarios here, as I mentioned. So use the encoder only if you have think like sentence classification, name entity recognition, etc. You're not generating anything, you're just processing the input. The decoder only when you are generating something, so that's the GPT family. And then you have the encoder to decoder is when you have sequence to sequence. So like, for example, translation, or the previous example I mentioned about taking a mathematical expression and finding the integration of it. Yeah, so I hope that answered the question. Yeah, that's kind of it. Yeah, so the encoder decoder initial was for that. That's actually correct. So if you look at the paper itself, in fact, let me open it. So if I just see here, so I'm gonna go to Dropbox. So yeah, in fact, the paper itself, if you look at the introduction, if you look at the abstract, they do mention that they propose a new simple network, etc., and their evaluation was about translation. So they used it was mostly about translation at that time. That's what they were thinking about. But then after that, they started to prove it's way more than just machine translation. Yeah. Cool. Yeah, so let's go back to this, and I hope this now is a bigger font, makes it easier to read. So we did have here some function to load the data, and you can see here some examples. So that's a sample statement. David Gallo, this is Bill Lange, etc. And then here is the translation that of the statement in French. So what we're gonna do is we're gonna try to encode these, convert them into some kind of you know, numbers, essentially, well, more like multidimensional numbers, and then feed them into a transformer, and then let's hope that with a reasonably large number of data, it learns to do translation. So let's see what's next here. Next here is we're gonna train a sentence piece, and that's going to be a new thing that I didn't talk about earlier. So sentence piece is a method of tokenizing input. And let me show you an example here before I talk about it. So, you know, obviously the idea is that when you have a statement, you want to break it down into multiple tokens. And this, let's go back to that diagram I showed you earlier from, you know, the pre-transformer age, where, you know, like if this is your statement, you know, like in this case, hello world. These, you know, you could tokenize and say I would like hello to be one token, comma to be another token, world to be another token, etc. And so you're going to have some kind of like, you're gonna say I have this dictionary containing say 8,000 words, for example, or 10,000 words, and you could put say the most used words, for example, in the dictionary, and then you could say, well, I would like to have a hard encoding of say anytime I get hello, I'm gonna give it the number 1, anytime I find world, I'm gonna give it the number 2, etc. But you can easily see the problem with this. It's like how many words do you have in a dictionary? It's like, do you want to put them all? How big your model is going to be? How it's going to be just massive. So the idea is that, and then you know you have verbs, for example, like in English, you know you have go, going, went, etc. Do you want to have all the ing or the ed for past, etc.? Just going to be uncontrollable. So people have actually discussed this and tried to come up with an idea of how to tokenize a statement and break it down into multiple tokens. And you know, there are multiple ways. There's like those who are in the NLP community might already know something about. We just also make this larger. So Porter stemmer, for example, that's was used. But let's see. To give you an example, that it tries to kind of like take all your tokens and then kind of like take the base form. So you can see you entered here code and coding and coder and coded, and they all kind of like end up being almost code except this one. So this one is used to kind of like, you know, try to reduce the dictionary size. But again, you see this is not going to work in machine translation, because you don't want something to give you the meaning of word or the base form of the word. You want something that actually, just make this bigger. You want something that represents the exact word. I don't want to end up having a translator that kind of like converts all my verbs into the base form, removing the ing or the ed or the past tense, etc. So there have been multiple trials to kind of like come up with a tokenizer. And interestingly, what they discovered they discovered can be useful is something from compression. So that's something that from Google. I want to show you. It's based on byte pair encoding, and that's kind of used for compression. So you can see, for example, if you want to compress this, how would you go about it? You want to have a text, and you want to say generate a zip file, or not necessarily a zip file, just a compressed file to make its size shorter. So one idea that they thought about is that, well, maybe you could find the most recurring two letter words, or two letter symbols or part of words, and then you could give it some different name here. So say Z in this text is going to refer to double A, and then you go after that, you do another iteration here and try to see which one is the more common one after you change everything to Z. And you can see it's actually now AB happened twice. So you say, oh well, okay, that's a common enough pattern. So I want to give it a one letter symbol, and then you change it to Y, and then you can see that your symbol is becoming shorter. And then you keep iterating until you end up with like this kind of form that is, that's the smallest possible. So you end up kind of like compressing all this into this, and that's how you make it smaller. And obviously you have to have a dictionary, which is common in compression methods. You have like a header at the beginning of the file which contains your dictionary of the most common of the most recurring patterns in your dictionary. Now obviously I can see you asking like, why am I all of a sudden talking about compression here? Well, this is they found they actually could use half of this process to tokenize the the input sentence or the output sentence, because the way is that at the end of the day you want to be able to kind of like have your machine translation try to understand the part of the words. That's what you care about. You want to be able to let your translator understand that ing is like a common pattern, that it should actually be its own token. So what that means is that when you have something like I am sleeping, you would like your tokenizer to understand that this is actually sleep plus ing. And interestingly enough, it happened to be that the case that you could actually apply a compression algorithm to go through your text and try to find the most recurring patterns. And then you could say, well, I would like to have a dictionary of size 16,000, for example. We don't refer to word anymore, we just say tokens now, because it could be part of a word. And then after that, you fix the problem of needing to have like a dictionary of millions of words, because you don't have to say every single word. You make your model more flexible, because it's just learning pattern than trying to memorize words and try to understand how for example sleep plus ing is going to convert to French. So yeah, that is an important part. And you can actually see here that when maybe that's not the best example here, because I'm only showing you the tokens. So what I did here is I trained a model. So in this code here, I took this package from sentence piece Google, and I do encourage you, by the way, to read this paper from Google. So yeah, take a look at this later. I think I'm gonna add it as a reference later. This is to share later. I'm just gonna add later and share it on Discord. So you can install this package easily, and which I have installed here, and then you can start to train it and say, well, I would like to have, say, where it is. So that's the sentence piece model. I'm giving it all the train and test data, etc., and then generating a file, which you can actually see here. So I'm generating like the whole corpus of the English and French sentences, etc., and then just dumping it, and then I give it to that sentence piece and I say, okay, well, build a tokenizer for me that works with this. And then you can see, I think if I go to the vocabulary here, I think that yeah, so you can see it's learning something here. You can see that it's learning that there's like these are all frequent words. Obviously you can see special tokens for the start and end of sentences, etc. And then it's what's the size of the dictionary here, let's see. So 32k, that has, yeah, that's what the size I use for the this example. Yeah, anyway, so long story short, you can see now that after I trained my model here, and then using this one, I train it and give it the data and say, just train it. It generates some files for me here, which contains the tokenizer. And then you can see later, I can actually just give it some sentence here like hello world, and then I ask it to encode it, and then I see these tokens. And I bet if I look at so let's see, 4832, let's go to 4832 here. No, sorry, it should be, I think it should be in the vocabulary. Yeah, so you can see that I did find my token here. It becomes a token here in the tokenizer. Let's see if we have any question. So, I thought I saw someone raising their hand to speak, but I don't see any request. So, is there still any question? Okay, I'll take that as a no. Okay, let's continue. So after that, now we can see that we have a tokenizer. We can start with the process of building the model. I mean, you can see that we have a tokenizer here, token function that takes an input sentence and then just use the source model we built in the tokenizer process. Then the other thing, obviously, is what we wanna do is we want what we call a statement boundary. So when you want to generate a statement, you want your model to tell you when it reaches the end point, the end of sentence. So you need to add special tokens to say, well, this is the beginning of statement, this is the end of a statement, etc. Because otherwise your model will just keep generating and generating and without stopping, and until it starts to generate like some nonsensical data. So that's kind of, again, that's part of the pre-processing of the data. So you add statement boundary. It's not rocket science. You just add the special sentences here, special tokens. Now the other thing is that is used, which is common again in training data, is called bucketing. So statement varies. If you look at this whole corpus, you see that you have like a statement of that's like 8 words, or with dot if it's using a dot, and you see much longer statements here. Now the idea is that you don't want to train your model sentence by sentence. You want to give your batches to the model. You want to give your statement to the model in batches and ask it to just learn essentially. So when that happens, you want to be able, you will have, because the length of statement varies, you have to make sure that you append them with zeros. So imagine, for example, we want to take these two sentences and we want to train them together. We want to feed them together to the transformer. We can't actually pass them like that, because at the end of the day you will have to have a multi-dimensional array, and what you end up doing is more like adding zeros here until they are equal. And by zero here I mean a token, not an actual zero as a text. So after you convert them, in fact, in this example when I showed you here that, for example, if say you want to train these two statements, and you can see one of them is of length 4 and the other one is of length 3, so you have to add another 0 here just so that they match. But having said that, you don't want to end up losing a lot of computation power. If you end up bringing together a very short statement with a very long statement, you're going to have to add way many zeros here, which means a lot of lost power, loss of computing power. So what they typically do is that they sort they bucket the training data into multiple sizes. So say a bucket of max size 10 and a bucket of max size 16, etc. And this is what I told you, what I promised you to go back to later in the session. So you can see I have bucketing here. I try to bucket statements of up to 8 together, and then up to 16 together, and up to 24 together, and so on, just so that so between this bucket and these two buckets, the maximum weight is like 7 characters, because between 8 and 6, otherwise if it's longer than that, it's going to go to the next bucket. And you can see that's kind of like helpful mechanism for training efficiency. So it has nothing to do in particular with transformer, just more like a machine learning technique. Right, so let's go back. So that's bucketing. Again, I don't think I need to spend a long time on this. You can read the code. It's no more than kind of like, a typical Python code that iterate through the statements by bucket, etc., and then by bucket size, and then by length, and generate different buckets. Now, obviously, other thing that we need to do as a pre-training is removing long sentences. So obviously you have to have a limit to your transformer. I mean, the bigger you make it, the more computation power you need. So it's always a good idea to say, well, I would like to limit my transformer to say, for example, statements of 512 maximum, for example. And Some of you might have already noticed this. For example, when you use ChatGPT, you can try it today and ask it to give you a very, ask it to give you something that is actually quite big. So a code to do, I don't know, some class to do some complicated stuff. You will see that at some point towards the end, it's going to be kind of like cut abruptly. And I imagine, I haven't actually read their code base to understand, but I would imagine it's happening here. They reach the maximum set of the transformer. So they have it, for example, configured to generate up to 2000 words. After that, they just stop. Yeah, so that's again, that's nothing super complicated. So it's just a filtering. Now, the other thing that we're doing here, again, that's typical of machine learning, not necessarily transformers, is to shuffle your input. And that's just to avoid things like biases where, you have like uninteresting example together, and then your model doesn't end up learning, good enough, etc. So it's a good practice to shuffle your data. And now the last thing that you see here is that we are combining all the pre-processing layers together in one layer that takes the training data, so take text, until it actually gives you a PyTorch array. And that's kind of like, this is kind of like summarize what I have been talking about here. So you can see that we take the training data here as text, and then you can see it goes through these multiple steps where it goes through the tokenization to break into multiple tokens, to break a hello world statement into hello token and a world token and a dot token, etc. And then you add the boundaries where, beginning of sentence, and then statement, and then end of sentence, and then you filter by length to remove the big statement or very large statements, and then you shuffle, and then you bucket by length. So you can have your data in a nice way that can be sent to a PyTorch model. And then after that, you can see that, now all of a sudden you have your data you can see as tokens here. So I'm dumping some sample here, and you can see the input statement ended up becoming just token numbers. So now my data is kind of ready to be fed into a transformer. And again, that's just printing some data here. Nothing, nothing like that. That's usually, I don't know whether it's just me, but I have that habit that I print my data before, multiple times, just because I want to know what I'm feeding into the model, just to get a better visualization of what's happening. Right. Now we talk about encoding, which is the part we talked about here. Let's see, in the transform model here, we said we need to have two encoding. One of them is the input embedding, and that converts, because what I showed you here is that I have token indices. These are not actually multidimensional vectors. These are just numbers that refer by the token number 9,799, etc. But I need to convert this into some n-dimensional space, so it could be like 512 dimensions, for example, and this is where the input embedding becomes important. So that's what I need to, and then the positional encoding to decide where my word is in the input statement. So this is the first word, second, etc., all these things, and this is where you see the encoding here. So positional encoding, and then token embedding. And in PyTorch, and I'm pretty sure every other deep learning framework, they do provide you a layer for embedding. So this is an X by Y matrix essentially. So you can see here that's the maximum length is going to be our dictionary size, because every token would need to have an embedding, and then the embedding size is just how big you want your embedding to be. Obviously, the larger it is, the more parameters you would require. And in my training, in my Jupyter notebook, I'm using an embedding dimension of 512. So every word can have up to 512 dimensions. So the way to understand what dimensions is say, for example, you have, back to our example from last week where we mentioned how like the word king, if you subtract from it the word man and add the word woman to it, you are expected to get in a good embedding, a vector that is closest to the word queen, because you're taking the word king, which means multiple things. Like, it has a dimension of being a man, it has a dimension of being royal, it has a dimension of being probably related to, say, for example, United Kingdom and countries which also have the royal family, etc. So these are all dimensions that describe a word. And the bigger the dimension, it means the more well, dimensions it could have. But here I chose 512. Obviously, you can choose bigger. It's going to be a bigger model. Right. So that's the embedding here. Nothing special. Just using the typical one from PyTorch. And in the positional encoding, I also decided to go with. If you recall, I explained that you could either manually craft it. In the paper here, they talk about they use a sinusoidal function here just to distinguish the index of the token, or you could just make it an embedding as well and just let the model get adapt to it essentially. Now we're talking about the most critical part of the model here, and you can see we're creating a model. I'm just calling it sequence transformer, and you can see what I'm doing here is, so I have a layer for the token embedding for the source word, the target word. I also have positional encoding, and I have the transformer here. That's the biggest part here, transformer. And what you probably need to look at most is the part, this one here. So you can see that what I'm doing here is I'm taking a source badge that's essentially multiple statements in a source language, and then I'm taking a target that's essentially trying to train my model, and then I am creating. So we need to talk about this create source mask a little bit, but at the end of the day, what I'm doing here is after I do the token embedding. So this part here, the source token embedding, is this one here, which is a token embedding, which essentially is this part, and this part here, the target token embedding, is this part in the decoder, and then the positional encoding is going to be the same for both of them. And then after that, I call the transformer and say, well, this is my input, this is my output, I would like you to do the forward call, which essentially is just going to return some output to you, etc. And what else? Let's see. These are the encode part and then the decode part, etc. That's just in case. I don't know why I added these two. I don't know whether I'm using them right now or just in the forward, but we'll see later. Right. So see if we have any question. Yes, of course, I can share the demo network. I'll just add it to GitHub and share the link so you can play with it. So yeah, I have my model ready now. I'm gonna talk about the mask later. Yeah, but for now, that's kind of like the gist of this. Well, this is the forward part is what you need here, creating the doing the encoding and then calling the transformer. Now let's see how we actually use this for training. So you can see I usually prefer to define the model and just make a call to it, etc., just to look at what it looks like, the model here. So I mean, I suppose I could open the full thing, and it's going to be slightly complicated, but if you want to take a look at it, you can. But you can see it has a transformer here, it has the encoder, and the transformer, that's of type transformer encoder, and you can see the layers here, because I have, if you recall from the paper, we said the encoder layer is actually multiple layers, so n multiplied by n. So if you want, you can have your model have like 6 layers, 12 layers, depending on how complex you want it to be. So you can see you have the transformer encoder layer here being generated 6 times. So I used a 6 time, just like I think that was their what they used in the original paper. Yes, that's and 6 identical layers. Yeah, and then you can see the decoder layer here. So again, that's 6 layers, and you can see, in fact, let's take a look at one of them. So you can see that what we have here is the multi-head attention. That's what we said here, this part here, and then we do the linear. I believe that's yeah, I don't know why the linear is showing here. I think that's not necessarily in the exact order, but you can see you have the layer normalization here. So that's, you know, what we talked about normalizing the output every time, just to make sure that our numbers don't become large and then becomes harder to train and deal with. Yeah, anyway, so you can take a look at this in detail, just to learn more about how transformer works and in PyTorch. But honestly, you might not need to go to bother that much, because after you understand how it works, you just start to use it. Just like you understand how, for example, you know, a chip works initially in university, but then after that you don't worry too much about understanding how every single bit moves at the transistor level. Yeah, so now that we have the model, etc., so that's another thing that I sometimes do as well. So I'm taking a source batch and target batch, and then calling the model here on the test source batch and test target batch, and this helped me with two things. So the first thing that it allows me to make sure that my model is working. So I'm giving it a source batch statement and then, you know, a target batch, and then I'm confirming it's accepting it with no errors. But also I would like to know the shape of my output here. Frequently, you know, you deal with a lot of shapes. Many of you might have seen this, I'm pretty sure. It's just become painful to try to match them, etc. So you can see that, you know, I just want to confirm, and as you can see here, so 10 is my batch size, because I sent 10, I believe here, 10 statements. You know, I took 10 statements from source data, and then 88 is the sentence size, and then that's this size, the dictionary size, if you recall. Yeah, anyway, now what do we talk about? Talk about beam search. Actually, I'm gonna skip this for now and come back to it again later, because that's more for the inference part. Let's take a look at the training part. So I have some checkpoints here, because it's a practice that whenever you're training some model, you make sure that you always have a checkpoint, just so you don't lose your the status. And the training here is where the big thing happens. So defining a transformer. Oh, actually, I wanted to show you something as well. Did I show you here? Oh, that's the number of total parameters. So I'm defined the model. As you can see, I played with it a little bit, and then I'm doing calculation to see how large my model is. So it's 93 million. So you can tell it's pretty small. Like if you're talking about GPT-3, it's 175 billion. So, and this one is just 93 million. So it's considered like a very small model. Yet you will see that it's actually not bad. It's quite powerful. So yeah, that's the model. And then during the training loop, what I'm doing here is, you know, the typical way of defining a loss function. You know, nothing special here. Cross entropy loss, and then my optimization function. So deciding how to change the parameters based on the gradients. And then the scheduler is just to play with the you know, the learning rate. So that's kind of like what you use the scheduler for. What am I doing here? So loading the model from checkpoint if it's already saved, and then after that getting into the training loop, where you can see what's happening here is I am going through the batches of the data loaders. So that's my, you know, that's going to be my training data. One thing that you might notice is that there are, so that's the encoder, the source statement, and that's going to be the decoder part. And you might be wondering, why do I have two statements for the decoder? And that's because, as you remember from the paper, the decoder actually also get the statement itself that's being decoded. And the reason for that is that it's actually shifted to right. So as I mentioned the other time last week, so if, say for example, let's see, I want to actually just use a practical example here to show you what I mean. So let's go to Google Translate and Google Translate. So let's take, say for example, I have a cat, and then I'm gonna use French. Jouer un chat. I don't know how to pronounce this one, but so that's going to be so your encoder is going to have I have a cat, and then your decoder is expected to have j'ai un chat, I think. Yeah, so that's going to be what your decoder is expected to do. But so what you're going to feed here is the output shifted right. So actually I just want to clarify that this will be more like something like this. That's the beginning of the statement, and that's the end of it. And again here, that's going to be the beginning of the statement, and that's going to be the end of it. So that's kind of like helper tokens we add. So the decoder will receive two statements. Sorry, that's one of them is going to be the input. The input to decoder is going to be this one here. Right, that's like this. And then the output to decoder is going to be like this. So essentially what you're saying is that you're telling the decoder, when I give you the sorry, that's beginning of statement. When I give you the beginning of a statement, I would expect to get the je. When I give you the je, I expect to get the a, etc., and so on. And the idea of this is that you want to be able to transform, to train the decoder or the transformer in parallel. That's one of the strengths of transformer, is that you can give it data in parallel. You don't have to kind of like give it one data in serial, which is very slow pre-transformer. So that's what it means to say that the shifted here. So you give it the data that's you give the same data twice. One of them is shifted to the right, and this is why we have two here. That's if you look at the data loader, we can take a look at it later. It does that for you and give you the encoder statement and the decoder, the source and target, and then after that the usual tensorization of your data, and then moving it to the GPU for faster training. And then what you do is that you run you can see now I'm running my model, getting predictions, but I'm feeding in the decoder source only, that part here, that guy. But I am expecting, when I do the loss function, I'm taking the predictions, and then I'm expecting them to be the same as the decoder target. And then I do the loss function, I do the backward back propagation, etc., and then normalizing the gradient. This is normal as well in training, where you just want to avoid your gradient becoming so large, so you kind of like do a clipping on them sometimes, just to maximize how big they are, to avoid your training becoming unstable. And then you do a loop here, just save it from time to time, and then after that every now and then I'm trying the model just to see how it's performing. So I do translation here, and I'll talk about what the beam search is. And then yeah, that's the main iteration loop. I run this before the presentation. I can show you that how it's working. So you can see that it's starting, doesn't have a saved model, and then during the training we will test with the following sentences. So I have this statement here, we had a marginal profit, I did, etc., and then this is the target statement, nous avions bénéficié, etc. yeah, so that's my goal here. I want to be able to, when I give it this statement, I want to give this statement here. And you can see that, I'm trying here. Predictive statement is now at the beginning. It just doesn't make any sense at all initially. It's just nothing to do with here with this one, obviously, because the model is still not trained. So trying to find a word from your dictionary that kind of like match this, but obviously it's not doing very well. But you can see here actually where it started. After some time, it's kind of like got the nous avons. It's wrong. It should be nous avions, but it's learning gradually, and you can see the total loss is initially high, but with more training epochs, you can see that it's just reducing and reducing. And I think I run it for 30 epochs. What's the minimum loss I got? So I reached 0.4 point 0.39, which is not a great, to be honest. I mean, I could run it further to reduce the loss, but it's actually a good enough one. And you can see that after that I tested the model, tried to translate a statement, how are you, and then it gave me, I think this is a correct translation. I'm not sure it's the best one, because I think sometimes the two in the French is referred to a single person, where I've seen sometimes in the French they use kind of like a polite form where you can they use vous to mean that you in plural as a respect. But I don't know whether that's kind of like a formal French or not. I'm not expert, but it's certainly giving you something, so it's learning. So yeah, that's the basic idea. I want to go back to a couple of points that I skipped over, and one of them in particular is the beam search. So what beam search is that the idea of the decoder is that it works in progress. So you give it the beginning, and it gives you the next token, and then you give it the beginning of statement and the next token and give you the third, and so on. But that could have a problem sometimes, in that it gives you some weird translation, because it's always following a greedy approach. So instead of trying to look at the bigger picture, it's just all the time try to take the best fit. So that's known to be like a greedy search, and it's not always ideal. So what they do sometimes instead is that they use beam search. And the way beam search works is that instead of getting the largest all the time, so I think this might explain it. And instead of taking the, let's see if we have Wikipedia page here as no. Yeah, so instead of always taking the largest, I don't know why it's not showing me the image I want. So instead of always taking, in fact, this look like could be something related, but yeah, instead of always taking the largest one, you take maybe say the 4 largest probabilities. So at the end of the day, the model is going to give you probabilities of next words. So take the fourth. In this case, the example is taking 2, and then from each example also take 2, and from each example also take the next, the highest probabilities, and among all of these take the best 2. So each time you go with like 2. So as you can see, it started with with a start token, and then A and C turn out to be the ones with the highest probability. So it has them here, and then from A and C generated all possible next letters, and now it figured out the highest probabilities, A, B, and AE. So it started, it went from there to next step. So this usually works better. In my example, I think I'm using 4 as a math candidate. So in each loop, I'm generating 4 possible next tokens, and so on until I reach the. So you can see that when does let's see, predictions. I think the loop goes on until it finds the end of statement, and then it breaks after that and say, well, this is what I found. This is the translation I found for you. Yeah, I think that's mostly it. I think I also want to talk about the target masks, and this one is a if you recall from the transform model, if you recall, this one was just a multi-head attention, attending to everything, so every word attend to every single word. But you can see that in the decoder they intentionally use a masked multi-head attention, and the idea is that when you are generating something, you don't know the previous you don't know what's going to be next, you only know the previous ones. But in training you actually know what's going to be next, so you kind of like intentionally apply a masking so that you remove all next tokens from the statement you send to the decoder. So that's kind of like why you can see that there's a masking here created on the target. um, but I think for the encoder I'm simply not using anything, so it's just all zeros. There's actually no mask here in the source, but it's just for to keep the code generic. That's why I'm doing this. And yeah, I think that's about it. I just want to see whether there's any question. Pruning node in search tree. Oh, so it's about pruning nodes in search tree. I mean, I'm pretty sure it has multiple use cases, but in the model which they call them autoregressive model, that's one of their use. So you might I can't recall now which source I found this in, but in some cases you might end up with, say for example, you're trying to translate some statement, and then you end up with something like your decoder generates something like this. No, 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 to you, because it's taking a statement, and then I mean obviously no is just here an example here, so it's trying to find always the maximum probability, and that happened to be some random word. And there was actually some examples with Google where you enter some statement and then it generates some weird output to you, because it's always trying to do the maximum. But I'm not entirely sure what you mean by pruning nodes in search tree. um, I would guess this is just dependent on the application, but in translation that's certainly the use for it. Yeah, I want to see whether there's any hello. um, so I saw a request from Mood Veric. I invited you to speak, but I don't hear anything yet. Okay, well, that's the request. Maybe it was a mistake. Yeah, so is there any question on this so far? I cannot speak. I cannot hear you. I don't. I didn't even see you here as a speaker. So I see, for example, now Palm Front as a speaker. Could you please say something, Palm? Interesting. Because like when I was speaking, I see that you can see that my name is not surrounded with like that green, which indicates I'm speaking, but I don't see the same here. Yeah, I don't know what's going on, to be honest. Okay. Yeah, so it's not just me then. I mean, I did talk to Tyler earlier, so I could actually hear him, so I don't think I have any issue particularly. Okay. Um, yeah. Yeah. So, any question? Anyone would like to go on stage and talk? How can we correlate this to the topics in the Learn AI Together Basics doc? Is that a question you can answer, Tyler? Because I'm not entirely sure which document Palm is referring to. Although I'm not sure whether Tyler is available, because he mentioned he might have to step out for us at some time. Yeah, I mean the honest answer is that I'm not too sure what document you're referring to here, but I guess if you can share it maybe, um, then I could maybe give some. I'll try to guess because I'm not actually part of that. Whichever committee that made that document. And I'm just gonna. I saw a request um to speak. Oh no, it's not anymore. It's not here anymore. Yeah, sure. That's definitely okay. I mean, I'm going to share the GitHub repository on the reading group, so you can obviously ask questions in the same group, in the same channel.
Test, test, test. I don't know if my mic is working at least.
Yeah, I had free test, so it's working.
Wow, great. Okay. Yeah, thanks for the presentation. I'm curious about the byte pair encoding, right? Do you think it might limit the system in some way when you like recursively replacing things of the words? And maybe that's why it's not good with rhymes and stuff,
um,
like
I
GPT
I wouldn't
systems.
I wouldn't imagine that it would be like a great limitation, to be honest, because I mean I haven't run experiments to compare, but if you think about it, like as a human, imagine yourself, you're trying to learn a new language, and then you start to kind of like detect patterns. So you see some words that like you see multiple words ending with like ing here in this example, for example. You start to think, well, is that a coincidence? And it can't be a coincidence. So you start to think, well, that seems to have a certain meaning in that language. And then you start to try to detect it, and then realize, oh well, that seems to be uh, changing the the kind of like the mode of an existing verb to mean something else. So if you think about the byte encoding, byte pair encoding, it's kind of doing the same thing, although for a completely different purpose. It's still trying to detect most recurring part of words. So, is it ideal? I don't think so. Because it might sometimes detect, like, I wouldn't be surprised if it detects a part of word that might not necessarily have anything to do with the English language, but or French or any other language. But I would imagine, considering that you have like a corpus of potentially hundreds of thousands of words, and you generate a dictionary of only say 32k words, it must have detected a good number of patterns that recurring within the statements. So yeah, I don't think it's going to be biggest limitation there. I'm not too sure though whether it works for all languages. So I know, for example, I think I was reading another research on translation, and I think it was English to Arabic, and then it was a little bit different. I think they used a different tokenizer, but I can't recall the exact details. So yeah, I would imagine it's not going to be perfect, but I don't think it's going to be a big limitation personally.
I was more thinking that, let's say, Rafitka, I hope I pronounced the name correctly. Let's say it's just three tokens, right? Because like the pairs of, let's say, Ra, Feed, and Ka, right? It's just three tokens. And then if I accidentally make a mistake in your name, a typo, For the system, it will be a completely different set of tokens, right?
Mm-hmm.
And maybe that's why like it's not good with rhymes because if the word ending is a little bit different, if it rhymes, but it's a little bit different, it might be a completely different tokens
Mm-hmm.
rather than just a small modification if it was just characters instead of like pieces of the word, you know?
Yeah, I see what you mean. Yeah, I think it is. I think considering how the frequency it aims to reach, I think that's going to be a little likelihood that this might happen. I think it's certainly possible that this might happen, but maybe with names or rhymes. I don't know exactly. I'm not language expert, but I have a feeling that it's not gonna be that frequent with actual words, because also keep in mind that you have a transformer has attention mechanism, a transformer has like embedding and all these things, so it has like multiple layers where it has information about your input sentence. In fact, hopefully maybe next week when we go through a BERT model from Google, what they do actually is that they play a game of close with the model, where you try. That's kind of like what you might have, many of us might have used to learn languages, that you hide you hide part of words and try to guess it, and you are able to guess it. So Google tried to do this on their BERT model and try to kind of like mask 15% of your text and try to let the model figure it out. So I think in theory what you're saying is completely possible. It might happen that you make a mistake and it changes, entirely changes the meaning of that particular word. But remember, it's not about just that word. It's about your whole sentence and the relationship between the different components of your sentence. That's my opinion again,
Yeah.
because I think with these questions, it's like without experimentation, I can't give you like an answer with confidence. But that's kind of like how I look at it. Cool. So let's see. Um, try to invite you to speak, Mood, but I think you might have to press something that you get the invitation and then you click. I think you have to click join stage. Oh, I see you on stage now, so maybe just unmute now.
Hello?
Hello. Hey.
Hello. Okay. Yeah, finally. Apparently, the header was actually conflicting with the accept banner.
Oh.
Uh, so I couldn't see the accept button.
Okay.
Yeah, I wanted to like respond to search. So for example, there are words which have exactly the same same sequence of characters, but different meaning in different contexts,
Mm-hmm.
right?
Yeah.
But transformers are apparently very good at detecting of which to tokenize in which things. So
Mm-hmm.
it won't get fooled even if the word actually have different meaning, even if it's has the same character,
Okay.
because it can look at the context.
Yeah.
So if it can do that, I think it can also fix the spellings.
Yeah, it can. Like, for example, if I make an error in the word understand, I think this error is very often being made, right? So, like, many times on the internet. And so
Mm-hmm.
the model will theoretically put the correct spelling and the spelling with the typo in the same embedding environment, right? Close to each
Yeah.
other. But it's like it's doing more work, right? If we just understood more on the character level, it would require more tokens, like the network would be larger, right? So it would be more wasteful, but maybe it would be even more, even better at languages. I don't know. I might do some experiments just
I
out of
think I think
curiosity,
that I
but
think
I'm interested.
there was a research that did try to do character level transformer. Let me try to see if I could find it. I think it was the guy is. I might have some difficulty finding it now. Character level language modeling with deeper self attention. I believe that's the one. And again, that so that researcher and this group were all at they're all at Google, at least when they published the paper. I don't know about them now, but yeah. So I think they would they did try to do character level language model. So I think that might be a good paper to go through. I did read it, but I can't remember the finding of it and whether it was like good result or better than doing like byte 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 pair encoding.
Oh yeah, that's cool. That's cool. I read it. Thanks. That seems like that's the
Yeah,
thing. Yeah.
let me try to share this one here. I'll share it again maybe with the resources. um yeah, so cool. Yeah,
I
no
wonder if
problem.
you just like at the closing, if you have any general advice on like how you stayed up to date with all the papers and everything.
Ah,
Maybe just like general advice to new people entering this field,
yeah.
and like because you have all the papers organized seemingly, and it's so much information. So
I
how do you manage all
mean,
this?
to be honest, it's just an impossible task. Like, I went to Europe's last year, and they were like, Europe as you guys pretty sure know, that it's like the top, or one of the top conferences in machine learning. So you would imagine that there's gonna be just a few researchers, but they had like close to I don't know 2,500 papers, and just going through the papers, like just walking through the conference area to look at the posters, was just an impossible task to cover all papers. So it's so hard. But what I usually prefer to do is that, like, I think the approaches that I take is that usually the papers take me, you know um to the next reference I would like to see. So, for example, I think I found this paper when I was reading the, I think, Bird paper, or one of the papers, and it had a reference to this. So I was like, oh well, that seemed to be an interesting idea. Um, and usually, what I like to do personally, I don't know whether you noticed, but in my papers, I save them by author. So initially it felt like an interesting idea, because, like, are you gonna memorize what each author did? But it actually helps quite a lot, because you start to kind of like develop a pattern where these people seem to be interested in that area, so they have research in that area. And that's actually something you notice. For example, if you go to I think it was Radford, for example. So the person behind GPT. So you can actually, once you see a person working on GPT, you start to think, oh well, maybe that's a researcher I would like to follow. And I think that's GPT-2, I think, paper. Yeah, I think that's GPT-2, and then you can see GPT-3 in 2021. Yeah, but another thing I do is that I try to summarize the papers, and then add a summary of them, add more like a literature review, because that's gonna help me have a summary, but also have, gradually I build a list of papers I would like to read next. So yeah, that's the way I do it. I don't know whether it's ideal, but it helps me up to a certain point.
Well, that's good advice. So like select top people in the field and mostly follow them, right? At least not to miss a paper from them. So
Yeah,
makes sense. Thanks. Yeah.
yeah, yeah. Um, Rabbit hole. I guess that's in reference to when I was talking about the papers in Europe, or is that? I'm not sure. I know what the context of that comment is. Yeah, so I see someone typing, but if anyone else has a question, feel free to make a request, and I'll invite you to stage, so you can talk. Cool. cool. Let's see.
Okay, maybe while I
Uh-huh.
start typing
Sure.
another one. So, what improvements do you see in GPT? Like for me, it's the context length, right? It's just too small, and would be nice to have like there are some papers that like want to do infinite almost context length, and there are some retrieval systems like Q&A similar to attention mechanisms, but they are doing manually, like by comparing embeddings to like a database of facts, and then pulling that into the context of, let's say, transformer, and then it notices it, right, somehow. So have you thought about this direction?
Um, so I'm guessing your question is like, what do you think can be improved over on top of GPT? Is that the question? Is like, what's next, essentially?
Yeah, like now
Um,
we're kind of in the limitations, right? So,
yeah,
so
I think what I see is what I see happening nowadays. I mean, again, I mean, I'm not like expert in all those researches. I know the basic idea, but I think what I'm seeing right now is more like improvement in the practical side of these. So, like you have a model, it's just generating some data, and it's not actually as smart as we think. It's at the end of the day, it's more like a generated that understand a large number of text. So what I see happening now is that they're trying to. I mean, obviously we know Chat GPT, for example, is um, was kind of like a modified GPT model with some reinforcement learning, but still it's not online. It's not finding anything for you. It's just stored in its database. Well, I mean, it's model. I think what might be happening, what I see happening right now, for example, with Microsoft and other people, is that they are trying to make it kind of fetch info from the internet, but that's kind of like more of an engineering application of it or practical side of it. Um, what what I imagine might, yeah, I that's what I'm seeing happening, but I don't know from the research side what might happen next. To be honest, I'm not sure yet personally.
I mean they're adding it to Bing, right? I don't know if anyone got access yet, but
I haven't,
trying to do
unfortunately,
like
but yeah, they are adding it. Yeah.
yeah.
Oh no, so I just want to clarify. I'm not saying only engineering problems are left. I'm pretty sure there's a lot of research areas happening right there. But I see what's happening in the industry is that they are trying to solve the engineering problems of it. But now actually one thing I wanna say that I would like to see is that these models are massive. So I think ChatGPT is 800 gigabyte. There's no hope you can run this on a commercial machine. It's just massive in size. You can't even have the computing power to just even do inferences. So I don't know. Is there going to be a situation where they optimize it somehow? That's an area I'll be interested in optimizing, models because they're just massive. Is there an active work on it or not? I don't know, but I hope. That's one thing I hope is happening.
I don't see at least OpenAI doing it,
Yeah,
considering how they are so, like against releasing them to the public.
yeah, that was interesting from OpenAI, if you ask me, because their name is OpenAI. They would like to make the AI open to everyone, so it's a bit interesting to see, Chat GPT-3 and not release and Chat GPT. So Open Assistant, yeah. I mean, initially they took some time to release GPT-2, but they eventually did. So I don't know. Are they actually now just worried about? Because their excuse was we worried about the misuse of this model, but they eventually after some time they released GPT-2. But GPT-3 was back in 2021, and it has been almost 2 years now. I can't remember the exact month it was launched. Um, I don't know. Are they gonna actually have any confidence at some point, or did they just change their mind? They want to keep it to themselves now. So I don't know.
I mean,
So this
like,
kind
I
of
think there's a lot of change in the philosophy of OpenAI, and after Microsoft had like large share of it, I
Yeah,
don't see them changing their philosophy. Well, there's a lot of paternalistic, I don't know,
yeah,
belief there.
yeah. Unfortunately, because because I think
What
they
about open source?
sorry.
Yeah, sorry. So I thought, what about open source, right? Because it kind of kills our hopes that our hopium that we can ever be playing with these models, right? OpenAI doesn't release GPT-3, of course, and we cannot train it by ourselves, even with these lectures, even with
Yeah,
Karpathy's lectures, we cannot train it on our hardware. But we do have like open source small models like 6 billion GPT-3
yeah.
or whatever. Maybe we can fine tune it and kind of train it more and more until um, it's on par or at least a little bit better than this. What do you think?
Yeah, I mean, I have tried to train some models. Like I took BERT for example from Google, and I use it to automate log log detection. So I want to be able to know immediately when some error logs happening, but I don't want to look at them as a human. So I did fine tune a BERT model on logs, and it was actually pretty useful. And I did it on my, I think it was my local machine. So. Um, but yeah, obviously BERT is open source and small enough that I could run on my machine. But with with GPT, is like it's not open and it's massive. So I have no hope of being able to fine tune it myself on. Unfortunately, it's just because it's. I think it's just unfortunate. Like we have no chance of dealing with those large language model as individuals. You have to be with like OpenAI or Microsoft or Google or
I
yeah.
believe Leon Institute is working on Open Assistant, which is supposed to be a competitor to OpenAI. They are accepting volunteers for the data sets at the moment.
Uh huh. Open Assistant. Which one is Open Assistant? I haven't heard
Yeah,
about
that's
it.
that's Yannick Kilcher. People might know him from his YouTube videos and the
Oh,
podcasts.
Lion. Okay, yeah. Okay, I'll take a look at this. That's interesting. But actually, now that you mentioned this, actually, Meta have. I think it's called Open language model. They have a language model that it's OPT. It's called OPT. So that's the equivalent of GPT. But so you can access the smaller version of it if you want. Down, but if you want the 175 billion, they only give it to researchers. So it's not actually completely open. But at least you have some hope that you can obtain it. And I would
They
imagine,
have
considering the size, it's just good enough, assuming
yeah,
you have the
they
right
don't
tool.
open 175 billion, but they open 66 billion model, and I played with it, but unfortunately, it's not close even to GPT-3 or ChatGPT, the
Yeah.
quality. But
Okay.
at least it's good. It's not output gibberish. Yeah.
Where are
Yeah,
you able?
ChatGPT. Yeah, go on.
Oh, I was just gonna say,
Yes,
where did you manage to run this 66 billion? What machine did you use?
it takes 128 gigabytes of VRAM, and so
120
I ran
gigabyte.
it on like
Wow.
run pod, so like rented servers. But unfortunately, it was a bit disappointing the results.
Oh, okay. So really, 666 billion isn't bad. So does it mean that the model isn't trained well, or?
I don't know. I just think that maybe they like OpenAI has much better data sets. Like they have thousands of people do like reinforcement learning from human feedback, right? Like on thousands of people. So maybe that's why
Yeah,
like the quality of
but
data.
remember that's the reinforcement part is only Chat GPT. GPT itself doesn't have any reinforcement learning, so it's just a transformer, huge one trained on massive data. So I don't see why Meta isn't able to do something similar.
Okay.
Yeah.
So they don't have well they mentioned Instruct GPT, right? And which is why it was like way better than just standalone GPT-3 or something.
Mm-hmm.
But I don't know. Like Instruct GPT, they specifically had a ROHF there, I think.
Okay.
But I
Yeah.
don't remember exactly.
Okay.
I thought the reinforcement learning part was simply to like modify the responses, not necessarily to improve performances.
Yeah, but I
Am
think
I wrong?
I think that I mean I did read their not paper, I think their blog post, but I understood that they actually modified the parameters somehow. So I don't know whether they actually have ChatGPT plus reinforcement learning, or and it's ongoing, or they had reinforcement learning to update the parameters of the model, and I think it's the latter. So I think it was actually used to improve the training itself, but I could be mistaken. They didn't talk much about it, I think.
Yeah, it's on the website, or in the paper rather, like the URL, and they show that basically instead of just doing gradient backpropagation from human feedback, which is like that would be too small of a change, they train a model that tries to predict whether a human will like it or not based on those outputs. And then the model,
Hmm.
and then the reinforcement learning model talks to the transformer model and improves it or something like that.
Okay, so it does update the transformer, right? It's not just on top of it.
Yeah, like a road chef goes into the reward model, like Pipa says here,
Yeah, I
and then
see.
the reward model is doing, yeah,
Struct GPT.
talking
Okay.
about the transform.
Yeah.
I thought that was simply with harmless, helpful parameters, right? It was not to like it does not change the raw power of the model. It simply makes it harmful. I think triple H. What was the triple H? Helpful, harmless, and there was
Hmm.
one more thing.
Okay. Yeah, I don't know. I honestly don't know that much. So I think that's something that maybe we should have like as a session in our reading group sometime in the coming weeks. That would be interesting to learn about. Cool. All right. Yeah. Well, I think we're pretty much out of time now. But I will share the material on the channel later. And if you have any where are the recording start? So I'm recording it, and I think Tyler is also recording it. So I think it will be uploaded to YouTube at some point, and then you can watch it again if you want. So yeah, cool.
Yeah, thanks a lot. Very interesting conversations we had.
Thank you, and I hope everyone enjoyed it. Everyone learned something useful, and hopefully we will see you again in next week with something more interesting. All right, have a good day, evening, based on where you are, and looking forward to talk to you soon. Bye.